Hi, everybody. Welcome to the podcast Everyday Metallurgy. In this episode, I have re-invited José Torralba, professor from Madrid University. He is an expert in materials called high entropy alloys and has been working on that for several years now. In fact, I invited him a little more than a year ago to tell about the materials. And at that time, it was a little difficult to understand the applications of it. So putting it into everyday metallurgy was maybe a little too early. But now I invited him again because a change has happened, not only in the world on high entropy materials, but also on Jose's view of it. So if you are interested in learning if these new kind of materials could have a place in your future life, then you should follow this. But enough for me. Let's take Jose with us on board. Hi, Jose.
Yes. Hi, Peter. How are you?
Fine. Thank you. And welcome to your second episode on the podcast of Everyday Metallurgy.
Okay. Thank you for inviting.
We recorded an episode about 1 year ago on high entropy alloys. And high entropy alloys is one of the fields where the speeder is really pressed hard. And a lot of things has happened just over the last year. The mentality of the people working on it has kind of changed, and they're not only looking at the standard way of defining high entropy alloy, but they are more looking now into high entropy materials to fulfill a need. And as I am one of the everyday guys who want to combine everything with how can I use it in my everyday. I had difficulties when high entropy alloy started, that just to mix 5 different things, but without having a purpose for it. Now it is really purpose driven. But Jose, before we go deeper into the future, could you sum up what is the definition of a high entropy alloy? How is it made, and how do you define it?
Yeah, this is a controversial point because there are many possible definitions. But in principle, high entropy alloys were developed in 2004, where two different groups, research groups, at the same time. It happens inside many times. It was a group from Professor Ye in Asia, in Taiwan, I think, and Professor Cantor in United Kingdom. Both of them previously they analyzed through thermodynamic calculation that it could be possible to stabilize a one single phase mixing at least 5 equi-atomic different metals. So this is in the classic conception of the metallurgy. It was a very difficult thing, because if you mix more than 2 or 3 alloys, two or three alloying elements with one base material, the most typical thing is that you will produce intermetallics or brittle phases in the microstructure, which are completely negative for the final properties. But those people predict that if you increase the level of the entropy, you will decrease the Gibbs energy formation for the single phase, and as a preferential way to define the microstructure against the production of intermetallics. So that means that mixing, in principle, 5 or 6 equi-atomic metals, you could have a single phase with a much better properties, because you introduce in the alloy other things that could improve the properties, as for instance, the biggest stress that you can have having different atomic size inside one lattice. So this is another thing, not only that. This was the initial definition of high entropy alloys, but very soon people start to say that it was not mandatory to have equi-atomic compositions, and there were even in the same year they were developed, there were people that start to define the high entropy alloys. If you have 5 or more elements, from 5 to 35 percentage, in atomic percentage in the mix. So it could open the door to have different alloying elements, but not in equi-atomic percentage. And after that, what we have seen, or many people have to see, especially in the last year, and that the entropy could play an important role in order to define the good properties of one specific alloy. And it was seen, it can be seen that even with one main element as iron, with several alloying elements, not concerned with 2 or 3, maybe 4 or 5 alloying elements, and not with any specific alloying element, it could be any alloying element, then the mix of entropy, it could be so high that can promote this single phase in this iron-based material or nickel-based material or any other. So that means that you can have materials, not high entropy materials, but maybe we can say materials with high entropy, which is not the same.
Yeah. So it has been driven a little away from this locked issue with the single phase or with the 5 equi-atomic numbers, but more into my field for applications.
Yeah, it's more interesting because it opens even another door that we didn't discuss before, is that you can take profit of any alloying element. So that means that you can construct final compositions using, for instance, scraps from different origins. That now in the field of the steels it was completely forbidden, because sometimes in one kind of scraps you can have copper that was not desired in a conventional steel. But with this philosophy, in which any element can contribute to increase the entropy level, you can use any kind of scrap. So we are open a new door also to sustainability recovery of any kind of scraps to produce an advanced material. So this is another interesting idea using this concept of high entropy.
Yeah, I remember when I was working at the Danish Steelworks, when we melted, we needed to dilute the scrap because there was too much copper in it, and if copper rose higher than 0.25%, then we had to dilute it with pig iron.
Yeah, for sure, because copper was something forbidden in some way in the conventional steels. But with this new philosophy, you can develop high entropy steels by using iron-based original material, but adding different alloying elements that can contribute to increase this entropy level, and in that sense to produce a good material at the end.
I have had difficulties in getting it into my head that if you want to mix different things, how do you know that it will perform? So what methods are there? Because there are millions of combinations. And how do you know where to look?
Now fortunately, we have very interesting tools thanks to the advance that we have in the communications and technologies and the informatic technologies. Today, we have the artificial intelligence and the machine learning, and also a lot of computing techniques to help us through modeling possible properties from one specific composition. So combining modeling, advanced computation, with artificial intelligence and machine learning, what we can, let's say, we can put in the same melting pot, we can put the composition with the expected properties, with other let's say, variables that up to today, it was not considered. For instance, the level of entropy is one of those. So we have to consider not only the composition and the expected property, but also the level of entropy. But also, in some of those new developments, considering the high entropy level of the mix, people have discovered that also other concepts like the stacking for energy in the system, or the lattice misfit, where you have gamma prime phases, or the so-called antiphase boundary energy. There are other concepts that can be applied for the design, to design properly the alloy. So we are in a complete very difficult situation because we have many 100,000 of possible compositions with the properties that we expect to have at the end of the process, with many possibilities for manufacturing. Don't forget that today we have powder metallurgy, but ingot casting, but also additive manufacturing of all the methods that in the market that you can apply, and also these new concepts like the entropy, the lattice misfit, all of those. Put all of them together, and you have millions of combinations. So the unique way is to have the help of the artificial intelligence or machine learning, and for that we have to train the system, and to train the system we need data. And to produce data, we have to use the so-called. There are many methods that we can call them high throughput manufacturing methods and high throughput characterization methods. And with those methods, we can produce many samples in not so a long time. And from those methods, we can get a lot of data to feed and to give a way to learn to the machine learning system. So this is the way that we have to do now.
Yeah. What about old databases?
Of course.
There must be a lot of data.
Also
in
databases.
articles.
Databases, because there are, for instance, the steel industry. You have millions of data that came from millions of casting processes during many years, where they have also the microstructure, the tensile features, the hardness, and microstructural features, all of things. The same happens in all the industries, in the super alloys, and you have a lot of information in the shape of data, also the scientific literature. But today we have tools just to capture those data. Today is much more accelerated, the data management systems in everywhere, in any place. I work, for instance, in my institute, we are working with ArcelorMittal, which is one of the big companies in Europe in the steel world. And they have a lot of, they are investment a lot in data management in order to put all the data produced in all the different labs, in all the different plants in the same place, in order to allow to those machine learning systems to use those data in order to learn and improve the materials. So this is another possibility, just to use all those kind of data.
Now we have the system. Now we can use it to design, and you said that their work on optimizing steel using not maybe high entropy alloy, but high entropy materials or materials with high entropy.
That's the idea.
But how do you do that? What are the targets in the steel industry? What are you targeting? Corrosion resistance, or are you targeting strength, or what?
In principle, any target, because today in materials we have to optimize as much as possible the raw materials that we have. We have to consider that in Europe we have a big problem with the raw materials, because many of the metals that we use are critical or strategic metals. So we have to take profit of any scrap, of any e-waste that we have available. And in that sense, what I am talking about is that we can mix any possibility of raw materials to produce an advanced material. In that sense, in the past, when we design an alloy, we start to design the alloy thinking in iron plus, I don't know, plus moly, plus nickel, or plus chromium. Okay? Today, the idea is completely different. The idea could be which feedstock we can have available in our surroundings. Which feedstock we can have, maybe from scraps or from any other possibilities. And using those tools, how percentage of each feedstocks we have to use to produce one specific material for one specific application. So then the paradigm has changed completely, because we don't start from one, let's say, a compositional goal in some way, in the sense that we have to use one specific set of alloys, of metals. Today, what we have to consider first is which kind of raw materials we have available in our surrounding, in order to develop, mixing properly those available materials, that alloy that we need to have strength and high temperature and corrosion, for instance. So this is I think the new mentality that we have to introduce. And the second thing is that we have to define our final target and our compositions very strictly in order don't lose any material in our composition. We need to take profit as much as possible of our design in order to avoid to waste materials, because today sometimes our designs are really wasting too much alloying elements for one specific application. So if you see, for instance, different series of aluminum alloys, sometimes we use the highest level aluminum series to just one application that don't really need this level of strength or this level of alloying elements. So today we have to take care, and these tools that I have mentioned can help to us to properly design the final material.
Okay. If we look into the big steel group that is called high strength steel, when I went to school, we defined that steels or most materials, they are on the material banana. So
Yeah,
you can have either high
yeah.
strength,
High strength, low ductility.
yes, but every material was on the banana. Uh, but over the last, I'd say, 20 years, there has been development of TWIP, TRIP steel that breaks this rule, where you can have both very long elongation and very high strength. And I also saw something on steel made with high entropy that fits into that. Well, is there any difference between a trip steel and a high entropy steel?
No, in principle, they take profit of the knowledge that we have regarding the trip steels or the TWIP steels, because at the end, what we are taking profit is the knowledge of the movement of the different planes when you apply the load to one specific steel in order to have better deformation. And for instance, you have mentioned the high entropy steels. There's a paper that was published by Dierk Raabe, which is the director of the Max Planck in Düsseldorf, that they really shows that using properly this concept of high entropy in the steels, combined with the stacking for energy, low stacking for energy in the system. If you have low stacking for energy and just one single phase FCC, you improve the twin effect or the twin effect in the steel, and then you will have not only strength but also more deformation. So what they do is to use in the design not only the old concepts regarding the composition, but also introduce this new high entropy, let's say, concept, and also the stacking for energy. So, but there is not only the stacking for energy, there are other concepts that you can introduce in the design. And for this reason, it's not easy to do it only with your mind. You need help. You need the help of the machines just to accelerate that. There is another interesting thing. If you optimize also the processing today, we can reach much higher levels. There is another paper from Raabe, it was published in 2023, that using just iron with a few manganese and some silicon, that means maybe I think in that paper they use also vanadium, a little bit, but not too much. Using a very small amounts of different alloying elements, and some of those as manganese or silicon, which are cheaper, very cheap materials and available materials, they can reach the top levels of the strength and deformation of the trip steels. So, but optimizing the processing, optimizing the forging and the heat treatments and the thermomechanical treatments. So we have a lot of space to run to reach the better properties today. So we didn't reach the better properties in the materials, because now we have much more possibilities to help us that can help us to improve the materials. I believe on that.
Yeah. We talked about the banana, and the banana is in fact what you can see here, this line. When I went to school, we only had materials on that line. We were told that it was not possible to have both, elongation and strength, as we have here at the bottom. But today, these new alloys has been developed, and a few years ago, I learned about the TWIP and the TRIP steels. TWIP is used a lot in crash absorption, and it has also been used a lot in military application because it can absorb a lot of energy during impact. Because the area below the curve, so if you take the curve here below, the area in this place, that is the amount of energy it can take. But if you look at these new high entropy steels that are being developed, wow, that is really a game changer. So the banana is a kind of rotten, isn't it? If this is possible. Back to Jose. Yeah. So if I in near future, I want more because today I'm working with a high temperature material, and I want that material to have a high resistivity because it's a resistive heater, but I want it to have a low heat conductivity.
Yeah, this is a big problem.
Yeah, but could that be a part of my wish list? I want it to be very stable at ultra high temperature. I want it to be easy weldable. I have a
Yeah,
wish list that is counterproductive today.
yeah. Also in the high temperature materials, this concept of high entropy plays an important role. There are papers that has demonstrated that the gamma prime solvus temperature in the gamma prime superalloys could be higher with higher levels of entropy. So it was a good correlation in between the level of entropy and the gamma prime solvus temperature. And also, in between the gamma and the gamma prime, you have the antiphase boundary. There is an antiphase boundary it has associated an energy. So looking for a high level of this antiphase boundary energy, you are putting more obstacles to the dislocations to move at high temperature. So if you introduce in your design those concepts, you will be easier to reach better levels of temperature. And then playing with the alloying elements, also you can also try to combine these levels of working at high temperature with other properties. But for this, I think the artificial and machine learning tools are really essential.
Yeah.
Yeah.
Do you have if we call these material for multifunctional materials?
Yeah, that's true.
Yeah.
That's true. This is the idea.
Are there any examples of multifunctional materials that has been found already?
Yeah, for instance, in our institute, we are working. This is more in not in the metallic field, but in the composites or even in the ceramics field. Now it's quite interesting to look for materials that could storage energy. And because if you can develop materials that can storage energy with low density, and at the same time you have good strength and good, let's say, mechanical properties, you can replace a lot of structural parts, for instance, in the airplanes, and you have to reduce all the weight which is established for the batteries. Because your let's say your structural material
is the battery.
Is the battery. This is one example in some topics that we are working now. So this is an idea that this is a typical multifunctional material, because the material is a material who has strength, but also has capability to storage energy. Also conductivity. Now also we are working in carbon nanotubes, and carbon nanotubes has a high level of conductivity because they are carbon, so they can conduct the electricity not as well as copper, but near to the conductivity of the copper in some way. And the density of those materials is 1/4 of the density of copper. So 1/5 is really much lower than the copper density. So if you can replace copper by carbon nanotubes, a composition of carbon nanotubes, not a composition, an extractor produced with carbon nanotubes, maybe you can replace tons of copper that you have today in a plane. So, and those materials, in that case, you are looking for a material with a multifunctional character because they have strength, but also conductivity. So there are many ideas about that. Of course, it's quite typical. When you are using a stainless steel, you have strength and corrosion. So also, an stainless steel in principle is a multifunctional material because you have two properties that are really complementary properties.
Yeah, that's right. I was also thinking on magnetic properties. In the magnetic world, you have hard magnets. They are permanent magnets, but they are called hard because they are very hard and they're very brittle. And then you have soft magnetics that also by nature are very soft. So in both ways, it's difficult to use those materials for design, or so you always have to build an engineered structure around it to support it mechanically. So
maybe this is one of the topics which is more difficult to face because there is a very, let's say, isolated family of properties. So magnetic properties is a family of properties which are not well combined with other possibilities. But also in this field, I am not a specialist in magnetic materials, but in this field, I think there is also room to develop things. And I am pretty sure that thanks to this modeling and artificial intelligence tools, we will improve in that field also.
I understood that the structure for a permanent magnet cannot be cubic. It has to be tetragonal to have the magnetic face, and it must be possible to have the artificial intelligence to search for such structures that has the tetragonal structure.
For sure, because even this let's say high entropy concept is also being applied for intermetallics. And intermetallics used to have a complex structure, not FCC or also FCC. Why not? But also different structures. And in that sense, I think there is also room in that topic because there are the so-called high entropy intermetallics that the idea is that you can use much more different elements in the two sublattices that usually has an intermetallic. In the conventional intermetallics, the two sublattices are made by two different alloying elements. But in the case of the high entropy intermetallics, each sublattice is compounded by different alloy elements, usually with high level of entropy, with a lot of different elements. So that means that maybe the properties that you can reach will be in another stage, much better in some way. And I suppose that in the magnetic field, in the magnetic area, also will happen.
Yeah,
so
absolutely.
Who knows? I don't know. There is a lot of things to do.
Yeah. If we look out in the world, are there today, of your knowledge, any application where an entropy material has been implemented in industrial use?
I think I have mentioned high entropy steels, high entropy superalloys, or even high entropy intermetallics. So I am pretty sure that in the future, when we will have to design an steel to compete with the maraging steel or with a TRIP steel, the way to compete with those steel will be using these concepts. So in the high structural steels, I think for sure we will use these concepts to develop new steels in the future. But also in the field of superalloys, both high entropy, conventional high entropy alloys, refractory high entropy alloys, today can compete with the best nickel-based superalloys. The problem is that the industry is not so easy to change the things, especially in fields like aerospace, which you need a lot of regulation. But it's a matter of time because the increasement of the temperature is really important. The temperature that we can reach using these new materials are relatively much higher than the conventional superalloys at some specific temperatures. So that means that it's a matter of time, because engineers, at the end, what they are looking for is for new materials that can jump to another stage in the application. So, and in this case, I think we have an important advantages in the two fields. One field is the high temperature, and the other one is the combination of strength and strain. So what you have mentioned, to be out of the banana curve.
Yeah,
So in
exactly.
both cases, these new ways to face the design of the alloys will help a lot to jump in these new areas.
Yeah. Do you also think that there'll be work on developing high strength alloys with low density, because it has been very steel dominated, but typical with a density around 7.5 to 8?
Yeah. In this case, also introducing light elements in the compositions, you will reduce density for sure. So it's also a matter that can be introduced in the equation in the design, in the equation of design. I think it could be also possible.
Yeah.
So in fact, in the topic of the superalloys, also is not so difficult to replace elements such as tungsten, or I don't know, elements with very high density by others. At the end, maybe you reduce 1 point or 1.5, but it's too much. So it's really important to reduce just 1 point in density.
Yeah.
Just working on just to replace one or two elements by another 2 or 3. And in this case, we have the complete periodic table just to use the design.
Yeah.
So this is the advantage of this methodology, in which you have a lot of possibilities for mixing. So what is important is to think that we are in a new paradigm. I am mentioning in the last time in many discussions that in the typical material science and engineering paradigm, we have the typical tetrahedron, in which you have 4 corners. One corner is composition, the other corner is manufacturing, other corner is microstructure, and the last one is performance. And compositions goes through the manufacturing to the microstructure and to the performance.
Yeah.
Today, we have to replace the composition corner by another double tetrahedron with at least 5 or 6 corners. One corner is the available feedstocks, which are the materials that you have available. Other corner, of course, is the data management that you can use to develop to feed the optimization process. Of course, the data that could feed also the machine learning tools. And there is another corner, which is the manufacturing, which is highly correlated with these 4 previous corners. So you have all of those is another tetrahedron by itself.
Yeah.
And after this stage, you have the microstructure. So it's a completely different way to define the microstructure. In the past, it was much more easier because you know the parameters for the forging or for the casting or for you know what happens when you produce those kind of manufacturing, even additive manufacturing, and you depart from one specific composition. And now it's completely different. You can have millions of possible compositions. You have to optimize those compositions with modeling, with tools of artificial intelligence. You have to combine these parameters also with your final target in terms of properties. You can put inside your tool those parameters, and of course the manufacturing parameters. And all of those constitute a different tetrahedron. It's another let's say set of combinations in between all of those things. And once you optimize those specific things, you will have a specific microstructure. So the paradigm is completely different than a few years ago.
Yeah.
Because all these tools also are new tools.
Yeah. And a lot of a big tool that has been used on standard material is to freeze it in a state that is not equilibrium.
Yeah, of course.
You can heat treat and rapid cool. You can quench and avoid the formation of ferrite and carbide, and form it martensite. So you make precipitation hardening to have small precipitates, but not fully coming out in to create equilibrium. Is
Yeah,
it
but
the same with these
today
materials?
is unbelievable the capabilities that we can have with the modeling tools, the thermodynamic modeling, that you can include in those models also non-equilibrium conditions. So it's not as strict that in the past. Today, even the capability to make different calculations are enormous. And today with CalFat, with program combined with Python, for instance, you can have in one day um, 1,000 calculations in different composition with different. So today the power of the calculation power that we can have in the computers are really high. So this will help us a lot to design.
Yeah. So are these new high entropy materials are they meant to be manufactured by a specific method, or is it optimized for that? Is it optimized for powder metal? Is it optimized for
Yeah, for powder
spray
metallurgy,
coating?
you know that I work on that, and powder metallurgy is one of the most suitable possibilities because today I have, for instance, one research line in which I am developing different high entropy compositions, and I'm also doing high entropy superalloys, not high entropy alloys only, also superalloys or other materials,
Yeah.
mixing commodity powders.
Mm.
So this is one line that could be that could approach to us to the recycling also, because mixing commodity alloys, I can reach many possible high entropy compositions by different combinations.
Mm.
What does mean? That means that I have the freedom to develop materials without the need to have one specific atomized powder.
Mm.
Because I can mix copper also, copper-based alloys
Yeah.
with cobalt-based alloys, with iron-based alloys, which are the stainless steel, with
Mm-hmm.
nickel-based alloys, with
Mm.
titanium-based alloys, aluminum. We have
Yeah.
plenty of commodity alloys in the market
Mm.
that can be mixed using this concept of high entropy to reach one
Mm.
specific goal in terms of properties.
Mm. So that can make it cheap because it's standard materials
This is
off the
standard
shelf.
material. I have developed, I have a work in the last months in which we have published it, in which we have developed the same alloy by mixing a nickel-based superalloy with an invar, with an iron-based alloy and a cobalt-based alloy in different percentages. And we have developed the same alloy by spark plasma sintering, which is a high advanced sintering technology, but also
Mm.
with metal injection molding.
Mm-hmm.
So it can be developed by different methods. Of course, you can do it also by press and sintering. Of course,
Mm.
density with press and sintering will be not the same
Yeah.
than in metal injection molding
Mm-hmm.
but if you properly select the size and the density, of course, you can
Mm.
in this for these in situ mixes are you need to have more or less similar densities or similar atomic similar size of the particles.
Yeah.
If you take care about that, you
Mm.
can use any system.
Mm-hmm.
Even I forgot. Also, we did it by powder-based laser system by additive manufacturing. The same material,
Mm-hmm.
plasma sintering, metal injection molding, and
Mm.
selective laser melting.
Yeah.
So it's possible to choose many possibilities.
Mm-hmm. And how does microstructure and performance change when you change process route?
Yeah, of course, microstructure is a matter. For instance, in the capability to homogenize the final microstructure is much better in a powder bed laser system because you melt the material and at the end you have a very homogeneous. But
Yeah.
in the case of metal injection molding or plasma sinter, we have to perform an annealing just to homogenize in some step of the
Mm-hmm.
process. But at
Mm.
the end, you can reach the FCC structure in both
Yeah.
of them.
Mm-hmm.
So it's a matter of to modify slightly
Yeah.
depending on the processing method.
Mm-hmm. So it's grain growth issues that can change the properties
Yes, of
more
course,
than
yes.
the microstructure.
Yeah, of course. One of the advantages of the powder system is that you are starting on a very small grain size from the powder. So that seems that in principle you can control better than in other processing methods the final grain size. So I think it's suitable. Powder metallurgy is perfect to develop such a kind of methodology, in my opinion.
Yeah,
Of course.
thank you. Yeah, yeah. Uh, yeah, we are both metal powder guys, so of
Yeah,
course.
for this reason is not a matter we always will talk positive.
Yeah, yeah. Jose, thank you very much. I would love to end on this positive note, bringing powder metallurgy at the forefront of the high entropy material development
Yeah, and
era.
advanced materials, not only high entropy, advanced materials.
Yeah,
We can do advanced materials using these kind of principles. Yeah.
yeah. And we have defined the new word, the multifunctional materials,
Yes, for
today as
sure.
well.
Yes.
Yeah. So let's see what will happen with multifunctional materials over the next years. I
Okay.
really hope that there'll be a big boom going on.
For sure.
So
I hope so.
thank you for sharing your insight. It was
Thank you for inviting me. It was a pleasure. Thank you.
yeah. Thank you. See you.
Thank you. Bye, Peter. Bye.
Bye. Thank you very much for listening. I really hope that you enjoyed it and you learned a lot. I did. High entropy alloys or high entropy materials or multifunctional materials, whatever you want to call them, seems to have a pretty interesting future among us. If you would like to learn more about metallurgy, you should follow the podcast Everyday Metallurgy on YouTube. It will be a pleasure for me if you'll follow it. It will enable me to reach out to a broader audience and to be able to catch the very, very high level experts that I would love to bring on board to share their knowledge with you. So follow the channel and sign up. Thank you.